three basic techniques for design analysis for algorithms. And the first technique is divide and conquer. Divide and conquer. We already saw two examples. The first, the one is counterfeit coin problem. That is, we use balance scale to find a fake coin. Okay, the complexity equation T of n is equal to T of n over 2 plus 1, meaning by using balance scale just once, we can reduce the problem size from n to n over 2, just 1/2. Okay, so that means this complexity is equal to log n. Log n. Why log n? Because the problem size becomes 1/2, then 1/4, and 1/8. Then it becomes constant after log n steps. And each step, we spend just one scaling. Okay, that's why it's log n. The next example is case smallest number problem. This is we are given n integers and numbers, then just find kth smallest, maybe fifth or seventh smallest or largest number. Okay. Then the complexity T of n can be written T of n over 5 plus T of like this. Okay. This is very important to notice that the problem size becomes n to n over 5 plus 3/4 n. Okay, importantly, n over 5 plus the problem size after it's divided into two problems. Divided into two problems. After that, the total problem size becomes this. And this is, okay, this is strictly less than n, right? So this is very important. This is very important. That's why, the total problem size becomes, something like 1/2, 1/4, 1/8, geometrically decreasing. That's why this value becomes linear, because problem size getting down, something like 1/2, 1/4, geometrically, and that means the total amount of computation is n plus 1/2 n, 1/4 n, geometrically decreasing. That's why this is linear. The total amount of the complexity is linear. Okay. Then the natural question is, what if this value is not strictly less than n? For example, what if this value is equal to n? Okay, this is our third example. Okay. So, I made a mistake. Yeah, I started this blackboard first, but it's not so good. Okay, anyway. Okay. So, example 3. closest pair problem. Our input is okay. So input is n points over two-dimensional Euclid space. So we have a two-dimensional Euclid space, and we have n points. It's a little bit difficult to have a good example. Anyway, okay. Okay, so it's a P1, it's P2, it's P3, 4, 5, 6, 7, and 8. Okay, so we give n points over a two-dimensional Euclid space, and our output is a closest pair. Okay, so 2 points Pi and Pj, such that the distance between P and Pj is the smallest among all the pairs. Okay, this should be clear, right? So in this case, what is the answer? Maybe this one. This answer. Okay. Now, okay, then there is an obvious approach. That is to check all N2 pairs. Okay, this is obvious approach. You check all the distances over this one, all pairs. Then of course you can get the closest pair easily. But the problem is we need order n squared time. Okay? So the goal is to design better algorithms. Better means which runs faster. Something like this is significantly less than n squared. Okay. So our algorithm is as follows, which is a typical typical divide and conquer. And this time, this is very important because this example is very important because in this example, this conquer part is important. In the previous examples, this conquer part is not so important. Just divide your problems to smaller ones, then you are almost done. So there's, essentially speaking, there's no conquer part. But this problem, there is conquer part. This part is more important than dividing part. What is conquer? Conquer means it's something putting two things together. Okay? So this is important. I'll show you in a moment why it's important. Okay? So, step 0. This is preparation. This is preparation. So the first thing we do is just sorting. Just sort endpoints along x-axis and along y-axis. Okay. So in this case, let's do that. If you sort this point along x-axis, then this guy comes first. So 4, 1, 3, 6, 7, 2, 8, 5. Oh. Is that correct? 4, 1, 3, 6, 7, 2, 8, 5. Yes, this is correct. This is sorted along x-axis. Okay. Now, if we sort those points along y-axis, so from here to there, then this is 5, 4, 7, 2, 3, 1, 8, 6. 5, 4, 7, 2, 3, 1, 8, 6. Okay. So this is the step 0. This is just a preparation. Then, oh, by the way, this is we can use any standard sorting algorithm. The computation time or the n log n. Yeah. This is you can use any standard sorting algorithms. Okay, now we are getting into the main part. Now this procedure CP closest point is sigma x sigma y of S. Okay, this is our procedure. What is S? S is a set of endpoints, of course. What is a sigma x? Sigma x is a sorted sequence along x-axis. So exactly this sequence. And the sigma y is a sorted sequence sorted along y-axis. Okay, so exactly this sequence. We have 3 inputs to this procedure, and our goal is, of course, this output of this procedure is closest pair. Okay. Now, maybe let's use this part. So the first step is just divide the point set into two halves, two subsets of the same size by vertical line, by a single vertical line. That means, in this case, here. Okay? So we use just single vertical line to divide the whole set into left side and right side. So this is S of L, S sub L, and S sub R. Okay? Of course, this is pretty easy. This is pretty easy because we have this sequence sorted along x-axis. So just just first half becomes SL, and second half becomes SR. So this is pretty easy. Okay? The second task is to sort SL, so left side and right side independently. So that means we need to get sigma x SL, sigma x SR, sigma y SL, and sigma y SR. Okay, we need to get four such sequences. Be careful. To do this, you should not use the standard sorting algorithms, because if you do that, then you need n log n time. But in this case, n log n is too much. We can do it just in linear time, because we already have Sx. We already have this sequence. Okay? So for example, what is this sequence? What is this sequence? This sequence is sorting this part. So this part along x-axis, that's exactly the first half of the sequence. You don't you don't have any complicated computation. You just take a first half of this sequence, become this. What is this sigma XSR? What is this part? This, of course, the second half of the sequence is S X of SR. Okay. What is this? What is this? This is sorted. This part sorted along y-axis. Well, this again not so difficult. Just look at this guy. This sequence. This sequence is sorted sequence for all S, But this is pretty easy, because if you look at the first point, 5, is this part. So 5 comes here, right? Then look at the second guy, 4. 4 is in this side, so the 4 comes here. We can continue this. Okay? So the next guy, 7, is this side, so comes here. And 2, again, here. And 3, here. And 1, here. And 8, here. And 6 here. Okay? Is it clear? It's very easy to get sigma y of SL and sigma y of SR. Very easy. You don't have to use the standard sorting algorithms, because we already have the sorted sequence for the whole S. Okay. So we need only linear time to do this. Okay. Now you understand that we are ready. We are ready to use the same algorithms. You know, the problem is already divided into two parts, SL and SR. So step 3 is just call SL okay. So we just call the same procedure for this part, S sub L, and step 4 the same thing. Okay? So this is a divide part. Okay. Now step 5. So we get two answers. We get two answers from this step and this step. So we have two pairs, two closest pairs on this side, and closest pair from this side. We have two answers. Then let's select the better one, just the better one. So just let okay. So we have obtained two answers from step 3 and step 4, and let pi xi yi be the better closest pair of step 3, and 4. Okay, and let delta is equal to a distance. The distance. Okay, I'm using this function distance with that definition, but it's obvious. Okay, this is the distance between xi and yi. So in this case, we already obtained, this one, 207 as better closest pair. Now, this is a question. Is that the correct answer? Yes, this is the correct answer for this example. But the question, real question is this always correct? Do you think this is always correct? No. No. In this case, in this example, that is correct. But for other examples, that may not be correct. Why? Just look at a different example. Just to change. Okay. To change this point to here. Okay. And maybe this point a little bit here. Then, this is a closest pair. But then again, the two answer is this, and I don't know. But anyway, this is no longer correct answer. right? So there may be a correct answer where one point is in SL and the other point is in SR. Now that answer did not come from step 3 or step 4, right? Okay, now what we should do is obvious. Let's try to find such closest pair. So this is the concave part. Okay. So we consider the following strip of width 2 delta. What kind of a so this is a vertical line. Between SL and SR. So this is a vertical line dividing SL and SR. And we consider this strip of width 2 delta. Delta is, of course, where? Yeah, this delta. Okay. So we just consider the strip of width 2 delta. Then there may be points in the strip. So like V1, V2, V3, and so on and so forth. Okay, there may be points within the strip. Now we look at the points in this strip from top to down, top to bottom. That means we look at V1 first, then V2 and V3, and so on and so forth. Okay, so this is this is SL part, this is SR part. And this is important. Vertical dividing line. Okay. Now, you're going to have very important observations. Very important observations. For the first point, V1, okay. For the first point, V1, we look at the rectangle of size delta by 2 delta below V1. Okay, what kind of a rectangle? Exactly this rectangle. Okay, this rectangle, meaning size 2 delta by delta. Okay, this rectangle is touching to V1. So below V1, we consider this rectangle. Okay. Now, important fact. Okay. A very important fact. If there is a point x such that its distance from V1 is strictly less than delta, then such a point x must be within the rectangle. I should have written rectangle. Rectangle. Okay. If there's a point x, which is a distance between V1 and x is strictly less than delta, then this point x must be in this rectangle. Why? First, x should not be here because this is V1 is the first one. Should not be here. Okay, this x should not be here. Should not be here. Why? Because if x is here, then this pair should have come from step, I don't know, step 3. So this is not correct. Okay, and x should not be here because it's obviously it's more than delta. So in this case, if V1 is on this side, then x must be in this not in this square. Okay? Anything is not clear? X should not be here. 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 It should be here. Okay? Good. Okay. The second fact is also easy. we look at any such triangle. Such triangle means 2 delta by delta. So we look at any such triangle. Okay. Delta, delta, delta. Then there are at most 6 points in this triangle. No more than 6 points. No more than 6. There must not be 7 points. Why? Okay. The worst case is this. This is the worst case. So there can be 6 points in this rectangle, but never, there is no 7th one. If you try to put the 7th point in this rectangle, then something bad happens. If you try to put the 7th here, then distance is less than delta. Okay? And if you so less than delta means, this pair should come from step 3 or 4, I don't know. If you put the 7th point here, then, this is less than delta, again, should have come from step 5 or 4, I don't know. Okay, so this is the worst case. You can put 6 points in this rectangle, but no 7th. Okay, clear? Good. This is the worst case. No. 7th. 7th point. It is possible to try to squeeze, try to put the 7th point. Then okay. So it is clear. It turns out that it suffices to check at most 6 points below V1 for possible x. Possible x means, the x the distance between x and V1 is strictly less than delta. Okay, what I'm saying is this is now you are looking at the first point V1, then just scan. Okay, the points in this strip from top to bottom, and look at 6 points. 6 points, and then to check the distance between that point and V1. If the distance is less than delta, then it might be a correct answer. Okay, so the important point is the 6 points are enough below V1. So just repeat this for V2, V3, and so on, and take a closest pair. That is our answer. So once again, if you look at the V1 first, then check the 6 points below V1 for possible correct answer. If there's a pair, less than delta, then it might be a correct answer. Then we go to V2. Then again, check 6 points below V2. Then go to V3. Check 6 points below V3, and so on and so forth. And of course, your answer is the closest pair. And this is the correct answer. Any question? No? Great. So we're done. We are done. And the problem is the complexity. The problem is complexity. So we have analysis. So T of n, okay. Okay, complexity of just a procedure closest pair, CP. And then we can write the equation T of n is equal to T of okay. Why? We are now excluding the preparation step. We are not counting. We are not counting this step. Okay, we are counting only the procedure CP. Then okay, this is step 1 is easy, very easy, and step 2 is linear time. Step 3 and 4 is this part. Step 3 and step 4. Okay. Because the size of a cell is exactly one half n. So this is step 3, and this is step 4, and this is again linear time, because no. So step 5 is obvious. Okay, just comparing two answers. So step 5 is obvious, and step 6. Okay, so this is a linear time. You can do this linear time because you have to look at only 6 points below VI. So that's why this step 6 is again linear time. So that's why step 3, step 4, all together. All the steps. All the steps is just linear. Okay. Then it is easy to see that this is n log n. Just you put n log n into this equation, then it doesn't give you any contradiction. So this is n log n. Okay, we are done. So our arrow is much better than the obvious one. Our trivial approach, easy approach, needs n square time, but this good one is only n log n. And it's a really good example for divide and conquer. Okay, so we need to conquer part, this part, step 6. Step 6 is really, really important. That is the conquer part. That means, only by dividing the problem into 2 parts, step 3 and step 4, of course, we can get 2 answers from step 3 and step 4, but, that is not a real answer. Not a real answer. You need to put things together. You need to put things together to get the right answer. That is exactly step 6. That is what we call conquer part. Good, good. Okay, now we are done with the divide and conquer. Let's go to the next technique. Okay, now our second technique is dynamic programming, DP. So, divide and conquer is very powerful, very powerful. For many problems you can use divide and conquer, and you can obtain good algorithms. But still, we have a good number. We have many problems for which divide or conquer does not seem to work. Okay, so for those kind of hard problems, this DP sometimes very powerful. So I'll show you what DP is. So I'd like to give you a basic idea. Basic idea of a DP, but this time it's not so easy to give you a basic idea in a single word. In the case of divide and conquer, it's pretty easy to explain its basic idea, just reducing the size of the problem, just dividing your original problem into couple of problems that are smaller than the original problem. That's the basic idea of divide and conquer. But in this case, now it's not so easy to give you the basic idea. Actually, it's probably some of you already know the dynamic programming. But actually, this is a fact. This is a fact that in my case, I first met DP long time ago. Then I was a little bit puzzled. I didn't understand why this is important, why this is good, why this is sufficient. Okay, so today, I try to give you my way of thinking about the basic idea of DP. That might seem a little bit different from standard textbooks. Okay, but I think that's much better than the usual explanation of DP. Okay. So we are going to the third example. No, fourth example. Okay. Yes. Now we're going to have fourth example. That is That's the equal partition problem. Our input and integers I sub 1, I sub 2 through I sub n between 0 and 100. Just like a test squads. Output. Okay. So our task is to divide those n integers into two groups with equal total sums. What does it mean? It's pretty simple. I'll show you a simple example. Okay, so that is the numbers. So that is 6 numbers we are given. Then your job is to divide these 6 numbers into 2 groups of the same sums, the same amount. Okay. In this case, I think if I did the correct calculation, then this is the one group. Okay, the sum is 130. Okay? The other guys, the sum of other guys should be 130. Is that okay? Yes. Yes, I think the sum of the other guys are also 130. Because that means, the size, the number of numbers with the 2 sides may not be equal. So in this case, one group has 2 numbers, the other group has 4 numbers. So we don't care the number of numbers. Okay? We don't care the size of the groups. Any application? I'm sorry, but I missed. I didn't give you any application about previous examples, 3 examples. But obviously, those problems are important. Yeah, and this problem is also very important. But it's maybe I'd like to spend maybe 2 minutes about application of this problem. Okay, so when I was a kid, it is very popular to play games. Like baseball, dodgeball, volleyball, it's very popular. So suppose that you have 15 kids. Okay, 15 kids, and they try to play baseball. Maybe some of you are thinking that it's impossible to play baseball with 15 people. We need at least 18 people, but for kids, that is not so important. Okay. So for example, if we have only 5 guys for one team, then this is a baseball field. Okay. It's a pitcher. It's the first base. This is the first baseman. And third base. Maybe we need some guy around here. Okay. So pitcher 1, 2, 3. Oh, we don't need catcher. We don't need catcher. Usually, we are not. Stealing base are not allowed. So we don't need catcher. Okay. So maybe the fourth guy, this is the second base. The usually fourth guy should be around here. And the fifth guy is around here. Okay, so only by 5 people we can do baseball. We can do defense. Because usually for kids, it's for right-handed guys, it's not so easy to hit the ball in this direction. So we don't need any guy here. Okay? So of course pitcher is important, and this guy is also very important, third baseman, because it's stealing balls usually come here, and the left guy is also important, but we don't need any other guys. So this is 1, 2, 3, 4, 5. So 5 kids are enough for one team in some case. That means we can divide these 15 guys into maybe 7 and 8, or 9 and 6, or even 10 and 5. Okay? The real question is to make a good balance between two teams. Exactly this problem, right? So you can put each player with a number. Put a number, kind of a score, test score. Then try to make, try to find, two groups, divided into 2 groups. Their total sum with scores are the same. So this is exactly this problem. Okay. Let's try to use the divide and conquer. Okay? So just divide and conquer is what? Divide and conquer is to divide the problem into maybe 2 small problems. For example, these 2 small problems. But this is obvious. It doesn't work. Okay? There is no such a partition for this group or that group. But actually, we do have a good partition for the whole set. So this is not a good idea. It's impossible to use a divide and conquer. So again, so let's consider the obvious approach as before. What is obvious approach? I'll show you in a moment. But in this case, this time, the obvious approach is just exhaustive search. So before explaining exhaustive search, let me change the description a little bit. So now output is a subset S. And such that okay, so now I'm using this definition for the output. Exactly the same. That's the same as before. Okay. So we'd like to find a subset S, subset S, such that their total sum, Z of S, is equal to 1/2 the grand total. 1/2 the grand total. Okay, this is the same definition. Because if you can find this subset, such a subset, then the other, it's a coset. Its complement. Its complement should be the other group. Its complement should also have the same sum. Okay. So this is the same definition. Okay. Oh, it's erasing. It's a lot of work. Okay. I got sweat. Okay. What is exhaustive search? Exhaustive search just look like this. We have a start. Then we try to make a tree structure for searching our correct answer. That means we first take I sub 1, the first number, then I1 we consider the two cases. The first case is I1 is in S. The other case is I1 is not in S. Okay? Then the value Z is equal to I1, and the value Z is equal to 0. Okay? Then continue. Okay? Okay. So we construct this tree structure to find the correct answer. So we first take I sub 1, then I sub 2, I sub 2, I sub 3, up to I sub n. Okay. Then you can see that every subset appears somewhere. Okay? So for example, here, z is equal to I3 plus I7 plus I10 plus plus in minus 1 or something like that. I'm sorry. Up to here, we didn't have I sub n yet, so maybe I sub 49. Okay. So all subsets of I1 through IN appear somewhere. All subsets appear somewhere. Then, of course, find okay. Then your task is obvious. Just find a node such that the z value is 1/2 the grand total. You're done. But this procedure has a big problem, namely not very inefficient, not efficient at all. Because okay, the number of all subsets, all different subsets, is equal to 2 to the n. Oh, this is a huge value. If n is equal to, for example, n is equal to 100, then it's completely out of question. Huge number. Okay. So this is bad. However, if you are a bit more careful, if you look at this structure a bit more carefully, then you notice something. Okay. Let's look at this level. This is, say, for example, this is I50. Okay. So you're now constructing this tree structure from I sub 1 through I sub 50. Okay. So you already have constructed this tree up to this level. Okay. Then, for example, this is I1 plus I don't know. There are many nodes. Okay. So, here's my question. How many different Z values are there? Okay? Suppose that this Z value is, I don't know, 1275, 78. Okay? So this is one Z value. My question is how many different Z values in this whole tree, or in this level? How many different Z values? Well, this is easy. You know, each number is between 1, 0, and 100. That means that the value should be between 0 and 100 times n. Right? We have n numbers. Each number is at most 100. Then the Z value is at most 100 times n. And that is an integer. That means the number of different values for z is 110. Right? Okay. Here we have come to up to I50. Then the Z value is between 0 and 5,000, right? But how many? How many nodes here? That is, what is 2 to the 50? Here, you know, this is binary tree. So the number of the nodes in this level is 2 to the 50. Is about 10 to the 15. Oh, it's a huge number. It's a huge number. So just imagine. You have 10 to 15 nodes here, but the Z value is only 5,000. Different Z values are 5,000. What does that mean? Okay, if you have 1278, then this might be again 1278. Right? There are many nodes having the same Z value. Then what would you do? You know, we don't need 2 nodes because that's the same number. So you know, you change this here. Okay? So you don't need this node. Okay? Because you know it's up to here, you know, there may be this path. Okay, so this path and that path is different, but making the same Z value. Okay, so from here, you know, only one case should be considered. So So the width of the tree, it's no longer a tree. There's a join. So this is no longer a tree, but its width is at most 100n, and the size of the whole tree is at most 100 times n squared, because the depth is n. Wow, this is not a big number for today's computers. Yeah. 100 times n squared is a small number. Yeah. You can do it up to maybe n is equal to 1 million. Yeah, to do the computer very fast. No problem. Okay, so this is a basic idea. This is a basic idea of DP. I think this is the best way of explaining the basic idea of DP. What you do is just exhaustive search. Exhaustive search by using this tree structure. Then you notice that you don't need that many nodes. You can combine many same nodes into one node. That is the basic idea of DP. Okay, maybe if you visit in some textbooks, then it's explaining this problem, the same problem. Maybe they're using this kind of table. Standard implementation. Okay, this is standard implementation is to use the following table. We say 0, 1, 2, 3, 4, 5, 8, 110. And the first number, I1, if I1 is equal to 5, then you put mark 0 and 5. That means that's the value, right? The value is 0 and 5. Now I2 is equal to 3. If I2 is 3, then what you do is just put the mark exactly the same place as before, here and here. This is automatic. Then you add 3 to this mark. So add 3 and add 3. Okay? So your second step. And third step, the same. Same. So you can complete this table. The table size is n by n, 100n squares. Exactly 100n squares. After completing this table, what you do is to look at some column that is yes. One half of the total sum. This column. If there is a mark, then that means you have a correct division, correct partition. If there is no mark, then the answer is no. So this is a standard explanation of a DP. But that when you first meet this explanation without anything about exhaustive search, then it's not so easy to get the basic idea of DP. Why it's good? You're just given this table. You can compute the problem. You can solve the problem. Yes, that's correct. That's great. You can solve the problem. But you don't know why this is clever. Oh, this is clever. But, once you know this kind of exhaustive search, but you can save a lot of nodes. Then you should understand why this basic idea DP is important. Yeah, good idea. Okay, great. So we are done about the first example about DP. I'll show you in the next week. I'll show you the second example of DP. Okay, good. See you next week.